Welcome back to ECE 501B. This is our last lecture together for the semester, and there's a few things that are due today. Actually, everything is due today. Your homework number 8 is due, and your project is due. There's one Dropbox, and you can now put deliverable 2 and 3. You can paste it together into one file, or you can deposit, I hope, both files into the same Dropbox. There are not two unique Dropboxes. You'll just put both of those into the one Dropbox. The TCE, Teacher Course Evaluation, is also due tonight. If you haven't yet done so, I would appreciate your feedback. This is not a direct controls class, but I appreciate feedback. I'm kind of a controls guy, so getting some feedback from the class would be beneficial. And just to reassure you, if you're new to this, I don't see those results, the comments, until a long time after the grades have been submitted or deposited in on your transcript. So it will not impact your grade, and it really is designed to help me improve the class in the future. If there are ways, and I would welcome your comments if you're listening to this at home, in the comfort of your home. I want you also to, if you haven't yet already, click on that link or fill out the TCEs. Hopefully this will be posted before 11:59 tonight when that TCE closes. The final exam, you want to make sure maybe sleep in that morning. It's a Tuesday, but it's a later Tuesday. We will have the final exam next week at 6 p.m., 6 to 8 p.m. in this room for those that are taking the exam on campus. The online students, it's your normal protocol. What I should mention before I get into the goals, so here's sort of the commercial for today, is office hours have been modified from the normal office hours. I will have office hours every day up until the day of the final. Tomorrow, I'm now delaying those office hours 1 hour from the normal office hours. They will start at 11:30. Friday, I guess maybe I'm anticipating you sleeping later for Tuesday. No, my schedule was in many double bookings, so this helps, I think, eliminate those. Friday is advanced an hour later into the day. They start at 11. And Mondays are new, since we won't be down here meeting. I'll be upstairs at 4 o'clock on Monday prior to the final exam. If you have questions, feel free to come see me during those time slots. If those don't work for you, send me an email and we'll see. But my days are kind of busy, full. The final exam process is similar to what it's been in the previous 2 exams, except you get, I think, 1 more sheet of notes. Did you have 3 sheets going into exam 2? Can't remember? Oh. Well, there's 4 sheets this time, just to let you know, and that's front and back, so you really have 8 pages. You can bring a calculator if it will help, something to write with, obviously, but everything else you don't need to bring. And the material is really from LADR. Have we used that acronym before? Probably not. Linear Algebra Done Right. So from our first text, that's where the material is coming from, and really up to the homeworks that you've submitted, homeworks 1 through 8. That's where the content will come from, and the final exam is comprehensive. It won't be multiple choice, I don't think. That'd be kind of novel, wouldn't it? Make it not, but that won't happen. Any questions on the final exam? And there won't be practice exams on D2L. Yes? How would I recommend preparing for the final exam? I wish I knew. I would focus on what you've done up to exam 2 because it is comprehensive, and now you don't have practice exam material beyond that. So I would then say, okay, let me start from exam 1, look at exam 2, and then start focusing on homeworks 7 and 8, the material in those. And then start saying, how can I work these problems in a different way? This one was a computational problem in the homework. Can I actually create a proof related to that concept? And if so, create the proof or create the theorem and see if you can now prove it. Or maybe it's in the book and now you want to try to come up with ways of creating proofs. I think practicing that, there'll probably be one proof at least on the final exam. That's how I would probably, and then I might start looking at the notes, and at the end, if you have an infinite amount of time or a little bit more time, then I would start going back into the book. But that's kind of the order that I would focus on: exams, homeworks, notes, and textbook. And it's all relative to LADR. As I said in the last lecture, lock the doors. What we do today won't be covered on the final exam. This is for your pleasure, today's class, hopefully. It's really to try to make the connection with what we've been doing, linear algebra done right, which is finite dimensional, extending that into infinite dimensions. Or what's the connection? How can we use the foundation that we've looked at in the linear algebra context to infinite dimensional spaces? Questions? Yes? I wish I knew. The question was, how many problems do we have? It'll probably be more than 1 and less than 50. Can we converge closer? How many have been on a final? Or on? We've had 5, I think, before. It might be more than 5 since you have 2 hours, but it probably won't. I don't think it'll be 10. Okay, so somewhere between 5 and 10 is what I'm guessing. Other questions? I'm not sure I can see all of the hands in the back of the book, back of the room, but I think I caught all of the hands that were raised. Unless you're raising your hand at home, send me an email. I probably won't see that hand being raised at home. Goals today, and actually these goals are not so much goals as more of an outline as to where you could sort of see the topics progressing through the second text. And we're not going to get through all of these goals today, but I'm hoping that this topical outline will start to, maybe if you see these words or see these phrases or see these concepts mentioned, you'll go, oh, maybe I can go back into this book, Signal Theory, and get up to speed on that based on what we've talked about in the first part of this class. For example, now we're talking about not tall, thin vectors, or we could think of polynomials as tall, thin vectors that are finite. They're finitely tall. Now what we want to think about are representing signals as sets. Similar to how you could think of these vectors, their endpoints or their head of a vector being points in this three-dimensional space forming a set. Now what we want to do is sort of think of signals, even though they are these two-dimensional waveforms, can we classify those to say, oh, that one is right here in this set. That signal is right here in that set, and if they're 2 arm lengths away from each other, they're a large distance away. But you can view these signals as like points or elements in a set, even though maybe you're used to seeing those as two-dimensional waveforms. Two-dimensional meaning time versus voltage or some amplitude. Or I should say amplitude versus time for y versus x. Once we've now sort of created these signals as sets, can we partition them? Can we do a... How did we partition our vector spaces? Did we have a direct sum decomposition in some cases where we had non-overlapping subspaces that we could then use and then write vectors in terms of? Now maybe we're thinking about partitioning these sets into partitions that are disjoint so that there's no overlap between particular sets of or subsets within this big set. So we're trying to create a more manageable set to work with, meaning the underlying set of signals might be infinite dimensional. You might have an infinite number of points, in a sense, as elements in this set, but now can we partition those to maybe have a finite number of subsets in this big, infinitely dimensional set? And that will involve then equivalence sets or equivalence classes. We'll then start talking about signal spaces. We have a set. Can we now figure out how to create a distance between elements in that set? That now gives us a metric that we can define, and there are many different metrics for the same set. So we could define several different metric spaces or signal spaces for the same set of signals, depending on how we define the metric. Once we have a metric, like I said, this is a long list, but I'm hoping that you kind of can see how these ideas would then flow in future exposure that you have to this material. Once we have a distance or a metric, we can talk about, are these signals converging? Are they getting closer to each other? Are they getting closer to an eventual limit? Then we can talk about convergence. We can talk about continuity. Have you heard about a Cauchy sequence before? If you now have two, or if you've labeled this sequence of elements in your set, and maybe it's labeled x sub n, a Cauchy sequence really says, is x sub n and x sub m, if we get high enough on that index, are those two starting to approach each other? That would be a Cauchy sequence. And if that's the case, then what can we say about the behavior? We can show that if we have something, and we'll try to define these a little bit, if we have a sequence of signals converging, they form a Cauchy sequence, but the reverse is not necessarily true. We could have a Cauchy sequence that's not convergent. I'll try to give you a little example in a minute. And then there's something called a complete metric space. And a complete metric, or the word complete, means that every Cauchy sequence, when these pairs of elements in our set, which these could be pairs of signals, when they're starting to get close to each other, when those converge to an actual signal in our set, then we say that the set is complete. We could have these signals converging, but they actually converge, their limit is outside the set. Then we would not have a complete set. Our limits could be outside the set. And that's, again, when it says convergent, our sequence limit belongs in the set. And here's what I had commented before. If you have a sequence of signals that are convergent, then those will have embedded in them a Cauchy sequence. Looking at them in pairs, those pairs would be getting closer to each other as you get far enough along in that sequence of signals. But you could have a Cauchy sequence that is not convergent. Let me maybe see if I can draw a picture. That might be a challenge, but let's see. Suppose that you now had, let's say this is time, and maybe we have that was supposed to go through the origin. Let's say this is now 1 over n, and this is minus 1 over n, so that's supposed to be symmetric. And now n we're going to let get bigger. Now, I'm not sure why I labeled it this way, because now I want to go to m, because that's another logical. But so let's say I go to m, and now this is 1 over m, and this is minus 1 over m. Do you see as the index gets big, this starts, it's remaining continuous, but do you see what the limit is? The limit is actually, let's say this is now minus 1 and plus 1. This would be a continuous function that the Cauchy sequence is converging. These are getting closer and closer to each other as m gets big. But in the limit, what happens? We reach this discontinuous function that's minus 1, and then it switches to 1. So you could have a Cauchy sequence that's not convergent. The limit is not continuous, so it's not in our continuous set of functions. That's sort of a counter example, or an example that illustrates you could have a Cauchy sequence that's not convergent. And if you want to look at this, let me see, where is it? This is actually example 2.6 in the text, which is, and now the text refers to our second text in the class. This is on page 25 in signal theory, that particular example. We could also divide these metric spaces up in different ways, different adjectives. We have separable metric spaces, which means that we have a countable covering. So 1, 2, 3, the natural numbers, but that could go on, but we can still always keep counting. Or we could have a compact metric space, which says that now we do terminate that number of coverings of our metric space. It's finite. If I now, and any time you see this linear adjective used in terms of something, linear spaces, what are you going to think? Relative to on the final, if you say, is this linear? Then you have additivity and scalar multiplication, homogeneity, that it's closed under those two operations. And when you start combining elements, linear combinations of these functions, we're in signals now, you could talk about linear independence and linear subspaces. Remember what we talked about last time, which was Fourier analysis, right? Where we now have these sinusoids. Those are linearly independent, and we can combine those to represent many different periodic waveforms. This is progressing similar to how our book progressed. Once we started having these vectors and we started looking at them in terms of linear independence, linear dependent, we said, well, how do we measure their distance or their length? Can we norm these? Then there are concepts related to that for signals. And maybe that involves integration. Maybe we can take the absolute value of x minus y, if those are signals, and integrate that. And that might be a metric. That would tell us a way of measuring the closeness of x with y. If x equaled y, Their distance would be 0 when you have x of t minus y of t. That was x of t minus y of t absolute. You could say, let me find x minus y and square that difference, integrate it, and then take the square root. Just for kicks, you could say, well, let me do that and do it in the L3 so that I now have that difference and cube it, integrate it, and take the cube root. And if you keep going, you eventually get to the infinity case. And we'll look at that hopefully in a little bit. Again, what I'm hoping that when you start seeing some of these phrases, you'll go, oh, he mentioned that on the last day of class. Have you heard of Banach spaces? No, well, you might. That's actually a linear space that contains a norm and it's complete. That means if you have a Cauchy sequence in that space, it's going to go to a limit that's in that space because the space is complete. That's a Banach space. It simply has a norm. But we then progressed and said, well, can we do more than just have distance? Can we maybe talk about angles? And we introduced inner products. We can do the same thing with signals. We can create inner products. And then we have, if a space contains or possesses an inner product, now we have an inner product space, where we're now looking at comparing two signals, two elements in the set. Then you can specialize these spaces one more level and say, oh, I now have an inner product space that is complete. Well, that's given another name. That's called a Hilbert space. And you may start to see that. If you're looking at different problems, they may say, oh, this analysis is performed on a Hilbert space. And that gives you some clue, oh, they have an inner product and it's complete. So now if this distance, which you can relate distance to inner products, because the norm squared you can think of as an inner product of a signal with itself. And we'll talk about, maybe, you may have to do this on your own, time ambiguity functions. So if you need a phrase to really impress whoever you see tonight, you can say, yeah, we were talking about time ambiguity signals, functions in class today. Maybe you don't have to use that low tone of voice. Maybe you can, never mind. But, oh boy, it's the last day of class. Looking at these, you can see that they're different, correct? Waveforms. But now if I shifted slightly these two signals in time, which one do you think would sort of be less ambiguous in terms of figuring out where you're at on that signal? Does that make any sense? So time ambiguity, if you have the ability, let's say that we were in communication and somebody said, oh, I want to send a pulse, and you measure the signal and you could relate this to autocorrelation, and you say, oh, I can actually tell that this had a measurable signal quantity at, let's say here, the origin. And the other one may, well, I don't know, that looks pretty consistent all the time that I'm doing this. So this has a lower ambiguity or time ambiguity in terms of trying to find where its peak is. If you now multiplied this times a shifted version of that, and if the time shift gets small, you can see that, boom, you're going to get a big peak when those two are aligned, and you're going to be able to definitively tell when that peaked. The other one in the top, if you slide it around on top, since it doesn't have a lot of fluctuation in time, it may be fairly ambiguous in terms of where's the shape. If you're looking for shapes, maybe you can't see it as well on that top one. And this again is discussed. I know you're going to want to run home and look all of this up. This is an example on page 33 in text 2 for the course. That's time ambiguity. Signal representations. This shouldn't surprise you, should it? We should be able to find a basis that we can now slice and dice, or what? Sort of weight a different signal or a signal from the set as a linear combination of our basis vectors. And if we have norms or inner products, we can now talk about orthogonality of those bases. If we have an inner product, that gives us an angle, and we can think what that means. Oh, these two waveforms have an inner product of 0. Those are now orthogonal. And we could use that inner product to find length, and now we can normalize these signals. We can now form an orthonormal basis. How do we do a Gram-Schmidt? The same way we did before. We just keep taking away components that we've already sort of built into our waveform. And so we can now find a Gram-Schmidt strategy for creating these orthonormal bases of functions from our set. That's the outline. And since we do not have time on the wall, we can go as long as we want, right? Hopefully everyone had a good meal before this. You're well hydrated, you're well fed, we can last a long time. So let's go. Let's see if we can get through that long list. Maybe not, but we'll start. Let's start by talking about signal spaces, where we're trying to sort of think about signals, again, not as these two-dimensional waveforms, or let's say voltage with respect to time, but can we think of this as like a point or an element in a set? Similarly to how you can think of vectors, if we're in a 3 space, you can think of each vector as the head of a vector coming out of the origin. And that now forms a point in that 3 space. And you can sort of visually imagine points being close. Now if we have a set of signals, can we somehow associate signals that are close to each other by viewing them as elements in that set? So we're going to start with signals and see if we can start to obtain some feel for thinking about signals as sets. Let's look at some examples. Suppose, and one that we're all familiar with in this discipline, I'm guessing most of you, since we're in the ECE building, electrical and computer, I'm hoping that we kind of are associated with electrical and computer engineering. One that we always play with is sinusoids as a signal. And so we could define the set of sinusoids, S sub S, where we might say, oh, those are the signals x such that x of t has the following structure. Maybe it takes the real part of e to the alpha plus j 2 pi ft plus theta, where t maybe goes from minus infinity to infinity, and t you could think of as time, and alpha, f, and theta, let's say those all belong to the reals. And you're going, well, that doesn't look very sinusoidal to me. Well, it's a complex exponential. And do I have everything parameterized properly? You could look at this in another way. You could say, well, that's e to the alpha, and then e to the j 2 pi ft plus theta. The e to the j omega t we talked about last time. That's this rotating phasor, which is cosine omega t plus j sine omega t, and we're taking the real part. This first piece, e to the alpha, for an alpha that's real, you can see that that's either big or small depending on what alpha is. And that's now influencing your magnitude or scaling of this group of sinusoids. That's a set of signals that encompasses quite a bit of practical signals that we could work with. Alternatively, we could say, oh, suppose that we had this set of sinusoids, but now we're going to give them an alternative property to make them a sinusoid, and you could say, oh, I want the set of signals x such that they satisfy the following partial differential equation. For some reason I'm having trouble with partials. But the second partial of x of t with respect to time plus lambda squared x of t equaling 0. Again, where t is between minus infinity and lambda is a real number. And so now, can we find x's? Well, x's that satisfy that are sinusoids. Again, that's another way of just writing, instead of drawing all of these sinusoids and saying, here's one, here's one, here's one, we can parameterize those and say, here's the set, and this is the set we're playing with. We could also have signals that were energy limited. Again, we're simply trying to find sets of signals and then figure out how can we partition these sets of signals. Here we might say, well, this is S sub e parameterized by k, where this is, let's say, the set x such that the integral of that function x, or the square of that integral, is less than k. Where this k is an element of the reals, and maybe it's non-negative. So that could be an energy limited signal. Another set of signals might be limited in another way. It might be limited in terms of time. So we might have duration limited signals, where this one now, let's say, is S subscript d on the parameter t, so that now we have x such that x of t is equal to 0 for all values of t greater than that index capital T. And a lot of times some of this just looks like notation. But what is this? This is really the set of signals that are 0 outside of time that's bigger than minus t and less than t. And if you wanted to kind of get cute, you could say, oh, I have a signal x that's an element of s sub d of t sub 1. And then you could say, well, that implies that x is an element of s sub d of t sub 2, if what? What's the relationship on these arguments? T sub 1 and T sub 2, if x belongs to the time duration limited signals S sub d t1, and that also implies that x is an element of the time duration signals S sub d t sub 2. What's the relationship on T sub 1 and T sub 2? Or, if that's sounding kind of Greek, why don't we draw a picture? So now, let's say that we draw this picture. Here's minus t1, and here's t1. And if x belongs to that, then x looks like that. And it's 0 everywhere else beyond that. This is now x of t. I'm sorry. Yeah, that's x of t that belongs to S sub d of capital T sub 1. Where can I place T sub 2 on this horizontal axis and make the top expression true? And again, you could say that, well, that's not the x. The x is actually, oh, I wanted it to be blue, but anyway. Now I'm right on the limit of that, but it still belongs to S sub d of T sub 1. Can I draw T sub 2 here? No, then x wouldn't belong to that. It's the last day. I'm just trying to play a little bit here. But now I think you can see that if T sub 2 is now bigger than T sub 1, we have that condition. And so now you can sort of start to see how you could create different sets that you could work with. Oh, I have a set of signals that are time duration limited by capital T1 and T2 and T3, etc. Another set of signals that we could use or talk about are bandwidth limited, or just band limited signals. In this case, let's say we now have S sub b of omega is now this set of signals x such that capital X of s is equal to this integral from minus infinity to infinity of x of t e to the minus j 2 pi ft dt. Let's say that that equals 0 for all magnitudes of f bigger than some frequency omega. So now if we tried to find how does x correlate with sines and cosines or sinusoids that have frequencies bigger than omega, it doesn't. There's no correlation. There's no frequency content in x that is bigger than omega. That's what this set is saying. So this is now band limited, and if you needed to draw that or sketch that, you could say, oh, I now have, let's say, my bandwidth. I probably should have drawn these later. But there's now minus omega and plus omega, and maybe my x of s looks like that. So that it has no frequency content beyond a value of frequency omega. Hopefully now you can see that there's a lot of ways that we can create sets of signals. And once we have sets that we can think of as elements in this set, we can start to do things that we love to do with sets. Now you can Is anybody having as much fun as I am? So what are we doing? Besides drawing Venn diagrams, yes, that's Venn diagrams. Now we can actually apply, if this was, let's say, S1 and this is S sub 2, or this is S sub 1 and this is S sub 2, do you see that in one case we might take the intersection of those sets, and in another case maybe we take the union? We can apply these set type operations to these signals. So now we can apply set operations like the union and intersection to these signal sets. As an example, suppose that we now have S sub d of t. What's that? Do you remember? This is time duration limited signals, the set of time duration limited signals, and let's say it's capital T. And now we, let's say, have S sub b of omega. That's the bandwidth limited set of signals. What if I look at the intersection of those? Now I want to look at a set of signals that are time duration limited and intersect that with a set of signals that are bandwidth limited. Can we say anything about that result? It's not quite empty, but that's basically what it is. It has a signal that's 0. So I won't call that empty, meaning empty would say there's nothing there, but we could have an all 0 signal and it would satisfy this, but nothing else. We can't have a signal that's time duration limited and bandwidth limited. It just doesn't exist. So this is now the 0 signal. This is the set x such that x of t is equal to 0 for all t. Meaning the only signal that is both band limited and duration limited is in fact the 0 signal. And the verification or validation of that, or the explanation, let me see if I can, for those that have been a little bit far removed from a signals and systems class, let's recall the Fourier transform. Now bar the doors. Recall the Fourier transform of a finite duration pulse waveform. If we now had the following, let's say that there's x of t, and it is a pulse of duration capital T, minus t to t, and it's only non-zero in that time interval. What's the Fourier transform of that signal? The kitchen sink. I mean, it's the sink function, not the kitchen sink, but it's the sink function, sine x over x, right? So this is now And where do I stop that bumping? I don't, do I? It's infinite in extent. We need all frequencies to make these sharp transitions, or to turn this signal off. If it's made up of sinusoids, we have to have all sinusoids present in that signal in order to have this time duration limited pulse, where this is now f and this is, since I'm going below the line, that's now x of f. Or we could say a non-trivial signal, a signal that is not just 0 for all time, a non-trivial signal cannot be both time duration limited and bandwidth limited. And I'm hoping that's enough explanation for that one set type operation. We're taking the intersection of two of these sets of signals. And we found that, in fact, the intersection of these two sets ends up being the 0 signal. Now that we have sets and ways of sort of collecting sets or finding intersections and unions, we can also think about how do we partition a given set. And there we might talk of the set of sets, meaning a set of subsets, where we might have S1, S2, let's say we do it up to S little n. And now the definition of partition really is sort of disjoint collections of sets. So the set of sets, S1 through S sub n, form a partition. Here's how we're defining partition. Of the set, where S is now S1 union S2 union all the way up to S sub n, if we looked at these sets pairwise and we formed their intersection, we would see that they are indeed the empty set. So now they don't share any signals in common when I is not equal to j. Or we could now, you knew this was coming, I had to be able to draw a cloud. We now have a cloud. Or, yeah, let's leave it at that. I was going to say maybe you're hungry and that looks like a pickle or a watermelon, or I don't know, whatever you're hungry for. Now I've got problems, don't I? Yeah. Okay, I'm not going to repeat that. One, I'm not sure I heard it quite, but we'll keep going. Here's one set, S1. Here is S sub 2, and let's say that we now have something like that. S sub 3, S sub 4, and S sub 5. They are dividing this set into disjoint sets, so we have a set of sets, S1 through S sub 5. And a partition maybe I didn't do it very well, but it's supposed to neatly divide a set. And you might sort of view that as disjoint sets. They have no overlap. Now you're going, well, how am I going to form these sets of sets? Well, sometimes forming what's called equivalence classes helps us. So now let's talk about what we mean by that. Often, it's the easiest way to get a partition is via an equivalence relationship. So now we need to define what it means to be an equivalent relationship or an equivalence relationship. Two elements, and remember, elements now, what we're talking about are signals. One signal is one element. Another signal is a second element. We want to say two signals, two elements of our set are equivalent if, and we need to sort of introduce a little bit of a wiggle here and there. You guys got such a kick out of the shaking yesterday or Monday or whatever. Whatever. This is now, instead of tilde, I'll call it a wiggle. So now x wiggle y really is just saying, meaning, or that's equivalent to saying x is equivalent to y. That's the notation if it satisfies a few properties. It's reflexive. X is equivalent to itself for all x. That would be kind of a challenge if it wasn't. So that one you kind of would think should be there. The other one is if x is equivalent to y, then that better imply that y is equivalent to x. So it doesn't really matter where you put these equivalence elements, on the left or the right, and that's true for all x and y. And finally, so that's symmetry condition. We have reflexive symmetry, and now we say that x is equivalent to y and y is equivalent to z implies x is equivalent to z, a transitive type condition. So now we have x is equivalent to z for all x, y, z. So those are the relationships we need to have true for elements in our set, signals in our set, to be equivalent. And what you might already be thinking is, wow, I could create all sorts of equivalence sets. There are an infinite number of possible definitions of what makes two elements or signals equivalent. All we need is the rule. All we need is for the rule to obey A, B, and C. The rule just has to obey A, B, and C. So let's see if we can apply this equivalence rule to see. Well, before we do that, let me just make the following statement. Application of an equivalence rule actually creates equivalence sets or equivalence classes. So you give me an equivalence rule, now we have equivalence sets or equivalence classes. And one more thing, if I now say that I have S sub x, that's maybe a set. I could say the set y such that y is equivalent to x. So all signals that are equivalent to x would form a partition. So now equivalence sets form a partition. Or the reverse is true. Also, any partition that you might create defines an equivalence rule. Now let's look at an example. What if we start with the set of integers, maybe from number theory? Now we're going all over the place, but now we're talking number theory. Consider the set of integers. I think we can all imagine what that is. That's now this set S, such that n assumes either the value 0, plus or minus 1, plus or minus 2, etc. That's now our set. If we now looked at that set of integers, mod 2, modulo 2, we could say mod 2 congruence generates how many equivalence sets? If I now separated if I had this set of integers and I said, okay, now I'm going to do mod 2 arithmetic on that, sort of what would you expect to see in terms of your sets within this big set? How many? Or is 2 equivalent to 3 mod 2? Is 2 equivalent to 8 mod 2? Is 8 equivalent to 20 mod 2? Is 20 equivalent to 21 mod 2? Is this making any sense? So hopefully you can see that really we're just dealing with 2 equivalence sets, even and odd, if we're doing mod 2 equivalence. So now we say this is going to give us 2 equivalence sets. S1, let's say that's the set of n such that n is equal to plus and minus 1, plus and minus 3, plus and minus 5, and etc. That we can see is the set of odds, and S sub 2, let's say, is now the set n, or set of n's that's equal to 0, or plus or minus 2, plus or minus 4, etc. So now if I give you an integer from this first set, you can hopefully pigeonhole it into one of these two sets. Is it S1 or S2? Where does it belong? And now we can partition this infinite set into 2 sets. What about another one? Suppose that we now say, here's another example, consider a set of all signals except for what is referred to in the book as the zero signal. It's not a signal that's zero for all time. It's actually what's being called the zero signal is really defined to be, let's say, S sub 0, which is the set of signals x such that x at time t sub 0 is equal to 0. So that's pretty restrictive. These are now signals that equal or have a zero value at or when time is equal to t sub 0. So now let's think of all signals that don't belong to that. And you could really say, just look at all signals. Think of all signals, and let's now think of the following partition. We can partition, or we can define a partition as follows. Suppose we now say S sub plus. That's the set of signals x such that if we looked at those signals, they would have a positive value at t sub 0 if we looked at time t sub 0. The other set, let's call it S sub minus. I think you know where I'm going with this. The set of x such that x of t sub 0 is less than 0. Think communications. If you were now in a communication environment and maybe somebody said, oh, I actually am going to have, well, those are kind of supposed to be symmetric. But now I'm going to look at t sub 0 and determine, did x1 get sent or did x2 get sent? And I think you can imagine that after it goes through some weird channel, you might have something that looks quite different than what you sent. But hopefully, when you look at t sub 0, you can distinguish between an x2 or an x1. That you can put all of these green messes into either the S sub plus or the S sub minus, based on what their value was at t sub 0. So this partition can be used to define an equivalence rule. For example, you could say x is equivalent to y, x wiggle y, didn't forget what that tilde is, x wiggle y, x is equivalent to y if we look at the value of x at time t sub 0 and we multiply that by the value of y. And these two signals are equivalent if they both belong to S plus or S minus. So what do we need this product to be? Greater than 0. So if both are in S plus, they'll both be positive. If they're in S minus, they'll both be negative, and we know the product of two negatives is positive. So x is equivalent to y if x t naught, y t naught is positive. That is how we could partition all these signals. What if I drew another example of that same set? Suppose that I now say something like the following. Here's time. And let me just start drawing some signals. Suppose I have F1, maybe I have F2, this is F1, F2, maybe this is F3, maybe this is F4, and what do I want? I need to now define, shouldn't have done it there, should I? I'll have one of those signals that I said was supposed to be missing, the 0 signal, wouldn't I, if I drew that too close to that place. And if you're following me, you know what I'm saying. If you're not, you're almost finished with the semester. Oh, you didn't have to laugh at that. Come on. Now that wasn't, well, yeah, you can laugh at that. So here, let me try to draw a t sub 0. That tells me some relationship, and maybe we only want to look at these between, let's say, A and B. We're not going to keep looking at these for all time, but now what does F1 belong to? S plus or S minus? Do you remember how we defined S plus and S minus? There's S plus and S minus. This is not rocket science, is it? But it's late in the day. Oh, we have our time back. The next stiff. I've been looking down too long. Sorry. If you're listening to this at home, you're going, would you? Well, you can advance this at any speed, right? When you're at home. So I'm sure you... Oh man, tough audience. Where's F1? That's S plus, isn't it? And what about F2? That's also positive at T naught. F3, that's the one that I was trying to confuse everybody with. But that's now negative, so that's now S minus. And F sub 4 is S minus. And I hope you can see then that if you took, or you could now say F1 is equivalent to F sub 2, since if we looked at F1 at time t sub 0 and multiplied that by F sub 2 at time t0, then it's positive. And F1 is not wiggle F3, since now if we take the product of F1 and F sub 3 at t sub 0, that's going to give us 0. So now we have a way of forming these equivalences, and we could also even make it even more sort of general. We can say, note that equivalence sets or equivalence classes can be represented by a characteristic element or member of the set. By a characteristic element, we could call that maybe x hat, meaning the set x sub hat is now the set of all x's such that x is equivalent to x hat. So now in the above we could say, oh, we could find s sub f1, and that's now all of these that have that property, or they're equivalent to f1, and it doesn't matter which element in the set we pick. So it doesn't really matter what x hat is, it just needs to be one of those signals or elements in the set. Does not matter which x hat is used. We had vectors, and then we had vector spaces. Now we have signals, we have signal sets. Now we want to talk about signal spaces. And what's that going to require? We have the set of signals. We have a signal set, or signal sets. And we need some way of telling how close these are, or some way of measuring distance. So now if we have a signal set and distance, that's now going to give us a signal space. And a distance, you need to be thinking norm, right? How do we find a norm? A distance definition, let's say D, is referred to as a metric if A, the distance between two elements in our set is greater than or equal to 0. So we have a positivity condition. And d of xy is equal to 0. When do we want that to be true? Only when x is equal to y. So we have some definiteness property. So, and d of xy is equal to 0 if and only if x is equal to y. So there's the first property of this metric or distance. The other one is if I measure from x to y, it better be the same as measuring from y to x. We have some symmetry. So the distance xy, it better not matter what slot I put these elements in the distance measurement. So now I have some symmetry. And finally, we need to have some geometric shape in this lecture. We need to invoke what? Our triangle inequality. So if we now say that distance of xz is less than or equal to the distance xy plus the distance yz. So now we have properties that this metric needs to possess, and we can start defining different metrics on the same sets. Suppose I now say, oh, here's d1 of xy, and I define that to be an integral from a to b of the absolute value of x of t minus y of t raised to the first power. And I'm going to now divide or take the first root of that, not do anything with it. That's now what could be called an L1 metric. Well, if that's the case, can I count? What's d sub 2? If I use the same structure, I integrate from a to b. But now when I look at the difference, or the absolute value of the difference, I square it and integrate that, and then take the square root. That's now an L2 metric. And that's what we're used to thinking in terms of metric, except now it's applying to signals. Another metric is, let's say, d sub infinity of xy. And since it's getting close to dinner time, this is the soup metric. All right, just humor me. But now sup is SUP, supremum. This is now what? This is taking the sup, or the least upper bound of the absolute value of difference between x and y. So sup is defined, or means, the least upper bound. Are we familiar with that? Least upper bound? If I drew a signal that, let's say, is x of t minus y of t, and maybe that is that, and I now see that there's 4. Do you see that if I just said an upper bound, I could call 7 an upper bound to x minus y's absolute, but I want to find the least upper bound, so the sup in this case would be 4 if I've drawn it accurately. Now that we have metrics and sets, we can combine them to get a metric space. So I could have one set of signals and combine it with D1. I could get another one. So that would be one metric space. I could get that same set of signals but use another metric, D2, and that's another metric space. I could use that same set of signals, use the sup metric, and now I have a third metric space. You can create a lot of different metric spaces with the same set of signals. We're out of time. We have to look at our sup menu. Maybe. I've enjoyed the semester. Hopefully you have too, but I'll see you in about a week for the final exam. Almost at this time. It's 6 o'clock to 8 o'clock on Tuesday of next week. Good luck with your finals. Good luck finishing up the semester. You don't have much time left. It's going to be done whether you want it to be or not. I've enjoyed it. Thank you.